So go ahead.
Okay.
You have the floor.
Hi, I'm Atsumoto from Nagoya University. Today I'm here to talk about a method for optimizing pipeline task-oriented dialogue systems. Okay. So the overview of our work. Our goal is to optimize the performance of pipeline task-oriented dialogue systems, even if the modules are not differentiable. We propose a post-processing networks, PPNs. As shown in this figure, PPN modifies the output of module to improve the dialogue performance. And we optimize PPNs using reinforcement learning. We conducted the experiments using the MultiWOZ dataset and confirmed the effectiveness of our method in both simulation and human evaluation. Here is the outline. I want to begin by explaining the background. As many of you know, a typical task-oriented dialogue systems take on a pipeline structure. For example, from this user accounts, natural language understanding module understand user intentions such as price is expensive and Wi-Fi is not required. Then DST module updates the dialogue state and retrieves entities from the database. Next, policy module. Based on the results, policy module decide the action to take. For example, inform users there are 30 portals and request the user preferred area. Finally, energy module generate the system accounts. Such pipeline system have several advantages, such as explicit input-output of each module provides high interoperability. Also, each module can be implemented individually with arbitrary methods, so easy to debug. However, pipeline systems have disadvantages that errors in preceding modules easily propagate to subsequent modules. So it is known to be vulnerable to irregularities in real dialogues, and overall dialogue performance of the system can be degraded. To address these problems in conventional methods, reinforcement learning applied to enhance the entire system performance. This method fine-tunes each module with rewards based on the dialogue results, such as task completion, as shown in this figure. However, there is a limitation that each module must be updated. So each module must be the trainable model. So these methods are not applicable when the system contains non-differentiable modules, such as rule-based and web API-based modules. This is exactly where we are focused on. To address this limitation, we proposed post-processing networks, PPNs. As shown in this figure, we install a differentiable network, PPN, after each module. And PPNs modify module output using the state of the entire system, like this. And we train PPNs with reinforcement learning to improve the system performance. So our methods can be applicable to systems, even if the modules are not differentiable. So now I want to describe the post-processing mechanism. In this figure, for example, PPNI post-processing the output of module I in turn T. In this part, PPNI and module I there, and the details are shown in this figure. First, as usual, module I produce original output. Then PPN I post-processes the O. Actually, the MLP in the PPN is the network that performs post-processing. We use an adapter to convert OI to the binary vector BI to input MLP. At the same time, we also create SI. It is a vector representing the state of module I. Usually, we use this BI as SI. But if we can get more detailed information, such as output probabilities, then we use it as SI. And not only module I, but also all the other modules at the same its state S. So we concatenated these and create this SO. We can expect that this SO vector representing the state of all modules, that is the state of entire system. So PPN can utilize this SO to perform post-processing suitable for the entire system. Now, BI and SO are concatenated and input to MLP. Then MLP output the binary vector B prime I. It is the binary vector with the same number of dimensions as BI. Finally, out adapter perform the opposite operation from in adapter to restore the O prime I from the B prime I. So this is the final result of the post-processing. We optimize the PPA post-processing by reinforcement learning. For the algorithm, we apply proximal policy optimization, a policy-based reinforcement learning algorithm. We let MLP in each PPN be a policy function. Specifically, we optimize each PPN by repeating this iteration. In each iteration, first we decide which module MLPs to be updated in this iteration based on the PPN selection strategy, which I will explain afterward. Next, we conduct dialogues between the systems and user simulator and accumulate input-output vectors and rewards of each MLP as training data. Once enough data collected, we update MLP using the training data with a specific universe size and number of records. We're repeating this iteration a predefined number of times. So PPN selection strategy. In our method, a system can contain multiple MLPs. So this means there are multiple policy functions for reinforcement learning. So we don't know which MLP, which policy function should be updated and in what order. So we experimentally determine which of the three strategies is best. First strategy is all. In all strategy, we update all MLPs at each iteration. The second strategy is random. In random strategy, we randomly update one or more MLPs at each iteration. The final strategy is rotation. We update one MLP at each iteration in order. We conducted several experiments to verify the effectiveness of our method. As dataset, we use the MultiWOZ dataset. We also use Convolute platform. The platform provides pre-trained models and evaluation tools for task-oriented dialogue systems. In evaluation, we use 4 metrics: term inform F1, match rate, and task success. Specifically, task success is whether or not the dialogue was success. So we use this metric for the reward in reinforcement learning. We use one user simulator using an agenda-based policy as a response loop. We conducted experiments on each of these 4 questions. First is, which PPN selection strategy is most effective? Second is, does PPN generally work for a variety of systems? The third is, how much does each module PPN contribute to the overall performance? The final is human evaluation. So does PPN work for humans as well as this simulator? To see which PPN selection strategy was better, we trained one system consisting of path-based NLU, rule-based DST, MLE-based policy, and template-based NLG. We use this configuration because especially MLE policy is used as an initial weight in many reinforcement learning methods. This table shows the results of the system without PPN. It is base system, and the system with applied PP with systems with PPN trained in each selection strategy. Overall, all metrics improve regardless of strategy. So it is indicate that the post-processing is effective. Next, the random strategy achieved the highest performance in most metrics. So in the following experiments, we will use the random strategy. So the next experiment is to our PPN work generally to a variety of systems. We built 6 systems, namely SysRule, SysMLE, SysPPO, SysSGL, SysRAR, and SysLAR, composed of various models available in CompLab. This table shows the results. For each system, the unchecked row is in the unchecked row is shows the scores of before applying PPN, and the checked score is after applying PPN. First, in these 4 systems, PPN includes all scores. In addition, in the other 2 systems, PPN includes some scores such as match rate and inform F1. So we can say that PPN works generally to a variety of systems. Third experiment. In the third experiment, we apply a PPN to only one module in the system. For the system, we use SysMLE as a base system, since it had the best score improvement among the 6 configurations in previous experiment. This graph shows the success and count for in the system, base system, and the system with PPN to only one module, NLU, DST, and policy. The final PPN plus PPN all is the system with PPN applied to all modules. First, the performance for the contribution, the scores of PPN all and PPN policy is the best got best improvement, and then followed by PPN NLU and PPN DST. However, overall, the PPN of any module improves the performance. The final is human evaluation. we recruited 40 cloud workers interact. We had 40 cloud workers interact with one of the 5 systems in experiment 3. So we totally recruited 200 cloud workers. This graph shows task success outcomes. First, for the performance, PPN policy has the highest improvement. And unlike the previous experiment, the PPN NLU has the lower improvement, much lower improvement. So that can be, we can say that PPN NLU may be overfitting to the user simulator. However, overall, the PPN is effective not only in simulation, but also in human evaluation. This is an example of dial in human evaluation. We check the first 2 terms between one worker and plus PPN policy. First, in first term, one worker said, I need a hotel in the West with free parking for 7 people on Saturday in the night. Then, the original policy does output nothing, but it is fair. So PPN policy modify and add some action, such as inform parking yes and request more. The next term, workers said again, can I book a room for 7 people for 3 nights on Saturday? So at the same time, in this time, original policy does not respond to the booking. So PPN policy post-processing and add the booking information. So the dial was successful. So in conclusion, PPN policy completed the actions that original policy missed. To summarize, we propose a novel optimization method for pipeline task-oriented dial systems using post-processing networks. We confirm effectiveness in both simulation and human evaluations. For future work, we plan to design more sophisticated rewards in reinforcement learning, such as module-specific rewards. We also plan to apply PPNs to NLG. Our code is available. Thank you for your attention.
Right. Thanks very much for your talk. So now we have 5 minutes for questions. Okay. Yes.
Testing. Hey. So if you wouldn't mind maybe generalizing a little bit and editorializing, what do you think the PPNs help the models do? Like, how would you describe the types of solution or types of situations that they corrected?
Sorry.
So just to generalize, like the PPNs were helping you in these different ways. Can you just tell us a little bit about what types of model deficiencies they corrected? What are they good at that the models themselves are not typically good at?
So in this slide,
Just looking for some intuition, like what information the PPNs bring into the system.
sorry, we didn't analyze the result. So how PPN generalizes the output, modify the output. So yeah, we should analyze their history more detail.
Okay. Any other questions? Over there.
Thank you very much for the talk. I was just wondering if you have one module and this module is fully differentiable, do you think adding post-processing networks then help, or you can also just say, okay, it's differentiable anyway, I can just directly optimize that module?
Yeah, it is one solution I think I thought. So in this time, we did not update even if the module is differentiable. But if we update, if system contains differentiable modules, and we simply fine tune this module by reinforcement learning, it is I think it can be strong performance. So yeah, it is a good idea that the hybrid of post-processing and simply fine tuning.
Just a small question, the reward you use is just task success?
Task success. This time,
Like the reward function that was used?
in tasks, for the task success, task success is calculated in two metrics. One metric is the system whether responds to user request, and the second one is the system provide correct entities based on the user constraints, user constraints. So the two metrics are completed, then the task success is completed.
Thank you.
Thank you.
Okay. There was one more question. Okay, okay, thanks. Okay, so I guess we can move on to the next speaker. So thank you again.
Thank you.
Is it every time you press the laser?
Yeah.
button,
Yeah, it was
really, really good. So also you could encourage people to stand here rather
right.
than there.
That's right.
So if
Yeah.
you move, and the point that this is